Okay, so we start the next session. We're going to 7.63. So continue with the sinusoidal signal model. Now we have amplitude, phase, and frequency unknown. And then as you know, we have more and more unknowns. We have more and more uncertainties, and therefore we'll expect more and more inaccurate performance. So when the frequency is also unknown, the GLRT decides H1 if this is larger than gamma. And this is what? P of X A hat uh, phi hat F0 hat divided by P of X H0. Or or we maximize this over P0. And then since the PDF on the H0 does not depend on F0 and is non-negative, we have this larger than gamma. Okay, so what that means is we have this, but we want to take the F0 out. And the way to take it out uh, is to just take the F0 that is the maximum for that and put it in. Okay, so max F0. Mathematically, this is equivalent to that because H0 does not depend on F0, so you can actually take the max out of the numerator to the whole thing, to the whole number, and then max P of this over P of X H0 larger than gamma. And because of the log is monotonic, we have the equivalent test. You take the ln, it's the same because it's monotonic. And again, because of the monotonicity, you put max inside or you put max outside and put the log inside. Log inside is a way to simplify it. It's a way to simplify it. So larger than that. But this is like that from the previous derivations. You take log that is equal to I F0 sigma squared. So finally we decide H1 if this is that. And this is again as defined by previous equation as the I of F0, which is the periodogram, or you think of it as a function. Either way is fine. Okay, so the detector decides that a sinusoid is present if the peak value of the periodogram exceeds the threshold. And if so, the frequency location of that peak is the MLE. Okay, so it's the two things done in one formula, right? Two things. What two things? Decide present. Present is H1. Non-present is H0, right? So you have one decision here. And the frequency location is the one that maximizes this equation. So it at the same time it gives you a frequency location. This explains why the periodogram or its fast Fourier transform is a basic component for narrowband detection. The detector is illustrated in this figure C 7.5C. Okay, its performance can be found in a similar fashion. So let's take a 7.5C. 7.5C, you have a received signal, and then exponent as a basis that comes in, and then you multiply it together and you get it into summation, and then you take the square, right? You take the square, you get parallelogram, and you choose max over f0. Remember that I as a function of f, if you are not choosing any value of f, then I is a function. A function is a function as a function of f. You cannot compare it with the threshold unless you give a value to f, and then the thing we do is we kind of do it max, right? Just recall doing max over f. In other words, you try all different kinds of possible values of f and try to find a max, and then you put it in, you compare with the threshold. If it turns out to be h1, then you say, well, that f0 that gives you the maximum I is the estimated f0. Otherwise, it will be h0. Then what happens in h0? In h0, there is no discussions about f because f doesn't even exist, right? In a signal model, f doesn't even exist. If this is h0, then it's noise only. Then there is no discussion about f. Okay, so I hope that we are not going too fast so that you can follow this easily. So maybe I should go a little bit slower so that you follow the page numbers. Okay, so its performance can be found in a similar fashion to that of the previous case of amplitude and phase unknown. So amplitude and phase unknown is going through this Kersey and chi-square discussion. Remember, we have this chi-square discussion when we are doing this amplitude and phase unknown. And now it's the same similar stuff as the amplitude and phase unknown. And then the only difference is that the PFA is increased by the number of frequencies searches over. Assuming an endpoint FFT is used to evaluate IF and then the maximum is found over the frequencies, we have that PD over this. In other words, it goes through some derivations, but we skip the derivations. We will say PD is equal to Q function, chi-square Q function with the degree NH square over 2 sigma square. And it's 2ln n divided by 2 minus 1 over PFA. Okay, so you have a PD as a function of PFA, that gives you the ROC curve. Okay? Okay, now we go to 764. You have amplitude, phase, frequency, and arrival time unknown. In a similar fashion, the GLRT decides H1 if this is true, if this statement is true. So you have P of X conditional A hat, phi hat, F0 hat, N0 hat. Now we have this S chart parameter N0 hat. The MLE of A, phi, F0 is the same as for the case of a non-arrival time N0 is set. Now the data interval is modified to coincide with the signal interval. So the MLE, right? The MLE. So now we calculate for non N0, meaning that we just first assume that N0 is known, and then A is equal to this alpha as the same as before. Alpha is the parameter, the received signal X multiplied by cosine and sum together. Alpha 2 is the x multiplied by sine, kind of a transformation, and multiply and then summation. So you get alpha 1, alpha 2. Now alpha 1, alpha 2 is going to give you estimate for alpha head. No, I'm sorry, phi head and a head, which has physical meanings. This is the phase amplitude, phase and amplitude. Okay. So now, see, we need this, and this, right? We need 4 items. Now we just assume that n0 is known, and then calculate a and phi. And then we go back to calculate f0. That's the frequency at which the parallelogram attains its maximum, the same as before. So we have, as in the previous case, p of this x, a, phi, f0, n0, and it becomes a parallelogram, where parallelogram is the same, right? Finally, to find the MLE of n0, we actually have we done this, right? We done this at 7 point somewhere, right? 7.5 or 7.4. We need to maximize this over n0. That's like a correlation structure we talk about. Remember? I think that this is what happens. If you have a signal like this, it's known. Then how do you know the time shift? Time shift refers to delay, right? So you do correlation with this time delay, or with a different kind of time delay, and then ultimately this one that fits better, the one that fits the time delay that fits exactly the same. When you do the correlation, this one and this one is going to give you the maximum correlation, because you see that that power only correlates and they may not be coherent, so they cancel out, they even cancel out. And this is the same here, right? And this is the same here, right? So ultimately, it's the one that matches the time delay. In this case, it will be this one and this one that gives you the maximum correlation. That's why when we do N0, we like to talk about correlation structure. In one way or the other, it's correlation. Okay, so finally, to find the MLE of N0 and maximize this over N0, equivalently, we decide H1 if this is the, and it has to be the max over N0, right? Or max over N0, F0. Or finally, if this is larger than that, and we decide H1. Okay, so we are done, right? You have X. Remember, you receive X. You're not sure about H0 and H1 yet, but you receive X. And then you do that. This is completely known. Okay? Completely known. And then you get alpha 1, alpha 2. And then you use alpha 1, alpha 2 to calculate phi and A. Now you want to do F0, right? You want to do F0 and N0. So you do parallelogram and then search for N0, F0 that gives you the maximum, and you compare with gamma. If it's larger than that, then you get what? You get two things done at the same time. First thing is you get H1, and then you get N0 and F0 as the values that maximize I. If smaller, then you say H0, and there's nothing to talk about N0 and F0 because they don't exist. Under H0, the signal doesn't exist, and therefore N0 and F0 doesn't exist. Okay, and this is just a definition. So you say you see it as a short-time parallelogram spectrum or whatever, but ultimately you can think of it as just function. It's functions. It's functions. Okay. So let's take a look the block diagram, you get this is a final cut. Right? Unknown amplitude, phase, frequency, and arrival time. And you receive the same thing, you receive x0. Now you try to do the exponent, multiplication, and summation. That gives you the almost that gives you a transformation, and then you take the squared, you take the square of the summation, and it gives you the parallelogram, short time parallelogram. And you choose max over this, remember, and it has to be done before decision for H0 and H1. Okay, this is important because this is a function of N0 and F0. Without F0 and N0, you are not able to decide the value for I. You are not able to decide the value for I, and therefore not to mention about the decisions. Okay, so you search possible N0 and F0, and it gives you the value of I, and you compare with the threshold and say H0 or H1, H0 or H1. If it's H0, then the max the values of F0 and N0 obtained here also generates the maximum likelihood decision for F0 and N0. If it's on the H0, then there's nothing to say about F0 and N0. Okay, so yeah, I think that's a block diagram. And also, let's see, we receive a sequence of X and do the sample number. It fluctuates. And then we are not sure about whether or not there is a signal inside, right? So we do a spectrogram, which is also called short time parallelogram. And you have frequency and sample number. N0, those two things are to be maxed, right? Yeah, to be maxed. Those are the two things that is to search for the max I. Okay, if I say it more accurately, those are the two things to be searched for the max xi. For the max I, for the to max I. Okay, to max I, and then I is the spectrogram. Okay, so you do spectrogram. In fact, it's just a calculation of this, and then you see F0, X0, there is a peak. So you take the peak and then compare with the threshold. Okay. So this is a GRT for unknown amplitude, phase, frequency, arrival time. Okay, and this is one is a time series, the other is a spectrogram. Okay, so if you put it in, this is called heat map, or the color shows the height up here. So it's a two-dimensional visualization for this part goes to the lighter color here, the lighter color, and you want to take the peak. So this is the GLRT of unknown amplitude, phase, arrival, and so on and so forth. So we'll just stop for the moment and we'll come back later.